Encryption is something that everyone knows they need, and it's only a matter of time before someone figures out how to crack it. And the coming wave of quantum computing means that we could face an Armageddon when it comes to all of the encrypted data that we've been using for the last decades. However, a new algorithm is on the horizon that would allow us to live in a post-quantum world. But is it something you need to worry about today? In this episode of the Tech Field Day podcast, we postulate that post-quantum and crypto is not something you need right now. Welcome to the Tech Field Day podcast, where we bring together a group of IT technical experts to discuss a single idea about key concepts in the industry. This podcast features a variety of perspectives from members of the Tech Field Day delegate community and is often recorded in association with one of our events. Tech Field Day is a part of the Futurum Group, and this podcast is also published on our sister company site, TechStrong TV. On this episode, we're headed into Security Field Day, and I'd like to take a moment for our delegates to introduce themselves before we jump into the topic, starting with JJ.
Hey, everybody, it's Jennifer Manella, JJ, security and infrastructure specialist.
I'm Alistair Cook. I'm a data center infrastructure and cloud guy, and now a part of the Tech Field Day team.
Hi, I'm Drew Conry Murray. I'm with the Packet Pushers. I've been covering the IT and security spaces for a long time as an analyst and reporter.
Well, thank you all very much for joining us. Of course, I am Tom Hollingsworth. I'm a practice lead and event lead here at Tech Field Day, part of the Futurum Group. Let's jump into the premise for today's episode. If you are a huge fan like I am of the seminal 1990s work Sneakers, you've probably seen what happens whenever encryption is no longer valid for anybody. Maybe it's a little black box in an answering machine. An answering machine, of course, was a thing that we used to answer the phone before voicemail happened. And it can immediately decrypt everything. Well, how likely is this science fiction concept? It turns out it's actually more common than you might think, to the point where the United States government has actually introduced legislation recently to force our National Institute of Standards and Technology, NIST, to adopt post-quantum crypto. But the premise for this episode is you don't need post-quantum crypto yet. All right, I'm going to open up by kind of throwing this out to the floor. What is it about current encryption that means we need to have some kind of a post encryption in order to avoid having Robert Redford read my emails?
So my understanding is that with the rise of quantum computers, they are very good at attacking the mechanisms we currently use today to develop the underlying mathematics of cryptography, which is basically multiplying two primes. Quantum computers are very good at that. It's not a hard problem for them, which is hard for more traditional computing. So the fact that quantum computers are, still on the horizon, but coming, the encryption community and industry realized they needed to get out ahead of this, so that when quantum computers are actually up and functioning, everything wasn't immediately able to be decrypted.
A plus, Drew, you must have watched my episode of Conversations about quantum computers as well as quantum resistant encryption, because that's exactly how I phrased it, is quantum computers are actually really awesome at solving and factoring prime numbers. And that's basically how RSA encryption works, right? Is that we have this huge product of two primes, and we don't know how to get that product. We get the factors of it easily. And that's why modern encryption works. That's why Bob and Alice can talk to each other. The problem is that when you have a computer that's strong enough and error corrected enough, you can solve that equation instantaneously and then immediately decrypt things. Granted, there was a little Hollywood magic in putting a little probe on the chip, and all of a sudden everything just kind of floats down like the Matrix. But that's actually a pretty good way to put it. And NIST actually had to come up with ways to defeat that didn't use traditional encryption methodology. So I kind of wonder, does this mean that the sky is falling now and that we have to switch everything tomorrow?
So as having a physics degree myself and having actually taken some quantum computing classes a very, very long time ago, it's interesting to me that what we see in quantum computing now is the ability to have a single qubit, the thing that does the actual math, take a set of inputs, generate a vast amount of possible answers, and then return the correct answer. The thing is, though, that qubits are really hard to build. They require sort of supercooling situation, and getting a computer with enough of them to do real work is the challenge at the moment. So it's that scalability of getting to the thousands of qubits that we're going to need if we want to break encryption. Hang on, I didn't want to break, but maybe if I'm a government agency, I do want to break encryption. To be clear, that's not what these computer systems, these quantum computers are being built for. They're being built because the same kind of math is great for doing things like forecasting financials and doing some material science, working out which alloys of what metal to put together. So it's not that these things were designed for breaking crypto, they're just extremely good at it. However, at this time, they're not sufficiently large in size to immediately break these large key sizes that we're using in crypto at the moment. But of course, everything gets easier to build as you build more of them, and the size of these quantum computers has been growing over time. And the challenge is when they're widespread enough and sufficiently powerful to deal with the encryption keys that we can generate now. Now, we can always generate larger and larger encryption keys, but the rate at which the quantum computers grow is going to be faster than we can handle those larger keys. So this is the driver for the post-quantum encryption ideas.
I love, I'm going to give the flip side of this because Alistair's coming in with this lovely accent and the academic approach. And you've got the lovely mustache, the little handlebar thing going on there. You look so sophisticated. So I'm going to lay on.
Lends credence to everything he says.
It does. And it's so true. But I'm going to lay on like rural North Carolina on you for a second. And, you know, the quantums, they just math real good. And really, all of our cryptography throughout all of time is just different math problems. Anytime we break encryption, it's a math problem. So the more speed and intelligence we have in the platforms, the quicker we break it. And this is just an extreme case of a big jump in technology in that processing power.
But is this really any different than when DES was supposedly an uncrackable encryption protocol, and now I can basically reverse it in minutes because the math factoring works out for even 56-bit keys quickly. And you know, technology is always going to march on. Like I can remember, you know, thinking about what it would take to brute force a password back in the day, and it's like, oh, you know, this could take years for you to factor it out. Well, at a big enough scale, cloud computing, for example, I can factor that password very quickly because I have what amounts to unlimited resources for a short period of time. How is using cloud computing to, you know, basically run John the Ripper to get into my email different than the kind of math that we would do to get, you know, an RSA private key?
I'm looking at the academic down here waiting for something cool.
Yeah, the speed at which we've seen growth in compute power has followed Moore's law, right? So we're looking at roughly doubling compute power every 18 months. I think we might have seen a bit of a slowdown. That's out to a whole 2 years for doubling. And that's what's killed the short key lengths and meant that if we doubled the key length, we can actually still do the encryption, right? We used shorter keys early on because it took a lot of compute power to do the encryption. As we start needing longer keys, then we have to spend more compute time producing those longer keys and the ciphertext from them. And so there's this arms race between the ability to attack the keys using large amounts of the same compute power that we're using to generate the keys. Where quantum comes in is that we sidestep that whole arms race, that quantum functions in a completely different way and scales in a completely different way. So if we're not using quantum to generate our keys, and I don't think anybody's talking about that yet, because you can't have quantum in your laptop yet in order to handle quantum keys. And so quantum is that quantum leap and the ability to decrypt, to attack these keys that's not matched with an increasing ability to generate keys. So if we went to encryption keys that were 1 million bits long, we'd have longer before quantum could attack them, but not as much longer as quantum will the rate at which quantum is going to grow in its ability to attack.
But you run into a problem there, Mr. Cook, and that is physics. Because if you make an encryption key 1 million bits long, I still have to calculate that key. I still have to do the math on a modern computer. And anyone who has ever accidentally typed in the wrong RSA key length on a Cisco router and watched it grind to a halt for 10 minutes because it's trying to calculate this is you know exactly what that is. Like there's a math problem that even the best CPUs today have a hard time calculating through shortcuts. Now, granted, once you've created that key, everything is copacetic. But like that's like my fancy MacBook over here, right? What happens when I try to do that on an IoT device? Like this is one of the problems that a lot of IoT manufacturers are starting to face, and it's actually something that I talked to Mike Nelson at Digicert about several years ago. Your thermostat does not have enough horsepower to calculate a reasonable encryption key, and that's with modern solved problems in this technology. Like once we get to PQC, like or post quantum crypto, that's a bigger problem, right? Like I've seen the technical specs behind this. There's like 3D lattice works and like multi-stage equations, and like I can already see the smoke coming out of my machine trying to do this.
Well, I mean, in the IoT world, we have ECC, so we've got elliptic curve crypto, which is much shorter keys. It's a much lower, it's just less intense from a processing perspective. So IoT devices can do that. But I think the other thing we're talking about, like PQC, post quantum crypto. Yep, Freudian slip there. Um, it really, it's not something we're worried about with every type of device and every type of data, right? We don't care if your thermostat data gets decrypted 10 years from now.
But at the same time, I mean, we kind of face this problem now where are there certain things that are okay to encrypt at a lower confidence level, if you want to call it that, whereas there are certain things that you want to have, like when do I use triple DES versus AES 56 256?
Every algorithm paired with key length and all of the other things that go with the crypto stuff has a certain shelf life, right? It's like a rating on a safe for or a firewall or something. Like how long will this last? Because hopefully organizations that are, mature and responsible and security conscious have data retention policies, and that data will have been destroyed digitally or physically before the shelf life of that encryption is met. So yes, there's certain types of data that we worry about for longer periods of time, things like financial data, government records, intellectual property, health records, things that people are keeping for a long period of time and need to stay private.
I think that echoes my feeling on it, JJ, is that the cost of quantum attack against your cryptography is going to be very high for a long period of time. And so the value of the data that I'm going to be able to retrieve through this quantum attack has to be very high. And it's that high value data that you have to protect more. And as you say, we've always been doing this. We've always chosen the level of effort for encryption that is going to return us some value. It's been really helpful to have offload. So having the hardware-based encryption in modern CPUs makes a huge difference to what we can encrypt. And what we will see over time, and I'm talking quite a long time, possibly my children's time, is where the offloads are actually quantum offloads inside these commodity equipment. That is definitely not a near future. That's a further out future. But it's continuing that trend of we're going to see more and more advanced technology available in smaller and smaller and more power efficient packaging. It's one of the standard parts of the IT industry, and particularly the hardware side of it, that we see more capability. And again, we'll go back to having an arms race where both sides are equal. When quantum attacks become practical, the arms race is going to be unequal because the attacks are going to be much more rapidly scalable than our ability to protect scales. So we're going to need to adopt something that is going to allow us to continue to compete with the attack capabilities.
Well, I think that's why it's important to note that I think NIST has released specifications for encryption algorithms that are resistant to the use of quantum computers, and they can be operated on the existing hardware that we have today. It doesn't require a quantum computer to use these algorithms. And so we're getting an initial level of protection against attacks using a quantum computer to decrypt encrypted information by using these new algorithms.
And one thing I want to bring up here, talking about NIST and this whole process to come up with these now poorly named algorithms because they all got a government number instead of something cool like, being named after crystals or something, was that they actually started this process fairly wide. I think they started off doing something like 60 some different algorithms, and over the course of the last couple of years, they've actually narrowed them down quite a bit. And one of the things that I thought was really fascinating was that one of the finalists that actually made it all the way through almost to the end, once people actually got a chance to test it and really dig into it, they found out that there was a shortcut that could have allowed it to basically be very insecure if it had been put into production, because basically there was a mathematical shortcut that allowed people to kind of dump the key. And I think that this whole process of putting these things out there for people to test has really helped us understand how difficult of a problem this is to solve when you're trying to make something that's resistant to what is effectively a magical computer. So, I mean, is this open sourcing testing of these things? Is this the way that we should do it in the future?
That's always how we do it. I mean, when we've had any type of, cryptographic algorithms like this, they are created and tested and peer reviewed by the community. That's how they get developed, and it's a lot of, smart people and interesting work around that space. I mean, one of the things at the RSA conference they did, because it was really centered around cryptography for so long. Watching that process a little bit play out on stage, probably, back when it was much smaller, more than 10 years ago. But no, I mean, that's how these things get developed. So yeah, they start with a super wide funnel. I don't remember when they started this, but I'm guessing it's, like probably at least 8 years ago, and they just keep narrowing down and whittling it. And then, as you narrow down, you have less of a pool for all of the rest, right? The whole population is split when you have a funnel of, let's call it 100 or 200. But then when you get down to the final 10 or 20, all eyes are on those 10 or 20, and you get just a lot more rigidity in the testing.
Putting my tinfoil hat on, I assume that, big governments around the world would love to have, private development of encryption and decryption tools that they just keep to themselves. But as, a consumer or a user or an advisor or a buyer, I would put more trust in models that I know have been released to the public and looked at by the public and looked at by various groups, as opposed to just, well, the NSA says it's fine, so it must be fine.
You mean like the news story from last year where certain government agencies forced a backdoor into an ECC encryption algorithm and then forced a whole bunch of network companies to use it so that they could decrypt traffic? And then it turns out the people they were decrypting the traffic from turned it around and started decrypting their own traffic. Not that that's happened before.
Hopefully we've learned, but I think we won't, and we'll have to go through it again and again. But my money for the best security is the one that has the most eyes on it publicly.
And I do want to bring up the fact for anybody watching this podcast who's rushing out to go download dilithium or kyber or whatever they call it now. We still have a point that we need to hit in quantum computing where this becomes feasible, because one of the problems we have right now, you've probably seen some of the headlines, of how many qubits Google has managed to wring out of a computer, which is impressive, right? But it's not just the throughput, it's the error correction, because quantum computing produces a lot of noise. And until we're capable of creating error corrected findings, a lot of what we get back is just noise. And so this whole completely invalidating RSA based encryption won't happen until the computers are, I think, what did I see, north of 50 qubits, but they have to have like a really amazing amount of error correction. And what that means effectively is money. Like you're going to have to invest millions upon millions of dollars into these things to be able to get them to the point where this can happen. Now, the flip side of that is that once that toothpaste is out of the tube, from that point forward, it's a problem. I say that if you are a company that owns a quantum computer or a nation state that has a quantum computer with appropriate precision, then yes, you could probably decrypt all the things that other people are running. But when do you think that that's going to happen? Because as Al pointed out, this is a physics problem right now. Eventually, it'll become a money problem.
Well, I mean, I think right now the focus isn't, or for most of us, right, on enterprise organizations and architects who are worried about security. We're not focused on we're not focused on quantum computing. We're thinking about post quantum crypto, which is how do we go ahead, because these algorithms are available to us now. products are starting to ship with them. We've already seen them in browsers. We're seeing them in switch route firewalls, all of the network infrastructure things. I'm sure they're into the, the clouds as well. And when we're talking about equipment and licensing that has sometimes 3, 5, 7, 10-year life cycles, we need to be asking our vendors at this point what they're doing for PQC and going ahead and implementing that, because it doesn't hurt anything. It's available to us. It shouldn't be an added cost or added work. We need to just go ahead and do it. And then we don't have to worry about what happens in 5, 10 years.
Yeah, there's, a lot of mathematical rigor that goes into the development of these encryption algorithms, but often where you get strung up is on implementation. And so we want to start getting, doing those implementation reps now before it really matters and before it's high stakes, so that we implement it correctly and learn how to do the key exchanges correctly and the negotiation correctly and write the software around it correctly, so that's not an emergency when suddenly we find out, oh, wait, X country has had a quantum computer for 3 years and they're grabbing everything and decrypting it. It's an emergency. Let's make our mistakes now while it's not an emergency. Let's start getting familiar with these algorithms, figuring out how they work with everything else that we're doing, get them into our firewalls, our browsers, and so on now before it's an emergency.
And I have to imagine all the various, compliance regulations are going to be mandating this anyway. So, there's PCI DSS for payment card, there's HIPAA for certain types of health records. And then we have all of the different layers of things for other personal identifiable information and financial transactions. Even just down to like the NIST suite, the NIST 800 suite that we use, the federal government uses here in the US, the 853, the civilians and all like universities. Like this is seeping down into our everyday lives in local municipal governments, education, of using these NIST, frameworks that are starting to steer towards, right, the NIST standards for cryptography. So that's going to be coming. That will probably come sooner than the actual quantum computing in a lot of hands.
I think it is important to recognize, though, that the quantum computing capability growth has been huge, and we've known that this was coming for some time. I think it was about 6 years ago I interviewed somebody who'd been working in quantum research at an event, and at the time we were talking about having the largest quantum computers having between 5 and 10 qubits available. Now we're seeing IBM last year had a quantum computer with 1,000 qubits. So we're getting to the point where there's enough qubits there to start doing that error correction and handle that noise. You do a triply redundant check of the math and you discard the one that doesn't agree with the other two. We are getting towards the point where the leading edge science can attack reasonably large keys and get good answers out. So we definitely need to be making these moves now. We need to be getting these experience, as Drew says. You need to learn this stuff. You need to start implementing it before it becomes the big crisis. But we are getting closer and closer to that big crisis now. It may be a year or two before we see commercial organizations able to do this. But I have this sneaking suspicion that there are government agencies, and particularly the unspeakable government agencies, both within the powers that we work for, but also the adversary powers, who probably have capabilities they're not talking about. And those are the ones that are most concerning.
And are happy to rent that out to help cover the cost, I'm sure.
Yeah, my concern is some of the long-term intrusions. I mean, we saw conventional long-term intrusions into power company, into telcos, not too long ago. Well, I'm concerned that there's more going on in the crypto side through undisclosed quantum innovation.
And I think that one of the kind of hitting on some of the points that you brought up here, the value in this is not that we've created a quantum resistant encryption algorithm, because there's hundreds of them out there. The value is that somewhere, someone who sets standards says, this is the one we're going to use, because this means that everybody can kind of say, we're going to use this, we're going to implement this. regulations can be rewritten to allow this in addition to other things. And yes, your regulation needs to be specific. It should not state like military grade encryption or something dumb like that, because first of all, that's not a thing. But more importantly, when you specify that, you know, you can either use something like AES 256 or whatever the NIST number is for Kyber, that will give you the capability to say, you know, I know that these workloads are protected at this time, and once we've started implementing this, we can iterate on it. And if we're iterating on this while quantum is still trying to break the stuff that we put in place now, that means that 3 years from now, when we finally get to a point where this is a problem, we are hopefully a generation or two removed from this. And whatever we have is even going to be more impressive as far as security and things like that, because this isn't always evolving situation. You know, like Alistair brought up, we saw a news story recently where, you know, a nation state actor used some pretty interesting ways to just basically slip into a telco and start siphoning data. And I believe, Al, in our conversation, our first thought was, you're encrypting data in flight, right? Like, if you're encrypting data in flight, this isn't a problem, right? You're doing this. And I think a lot of people aren't doing that right now, and they need to address that. Like I don't care which one you pick, but pick something. Because once all the data that was flying across the internet is encrypted in flight and it's very temporally sequenced, a lot of this doesn't matter. The value in using a quantum computer to crack encryption is not that it will take, you know, you'll be able to look at data from 10 years ago and get it. That's not very valuable. It's that you can decrypt in real time on the fly and basically intercept point in time communications.
Yeah, JJ and I did a podcast with DigiCert, and I feel bad about repeating vendor lines, but I think they did bring up an important point, is that what we should be thinking about is agility, meaning we're never going to be sort of one and done with the perfect encryption algorithm. So you're going to need to be comfortable with rotating in and out of encryption algorithms, making sure your systems and your processes are able to roll with the punches, essentially, as new algorithms roll out and new attacks roll out, to be able to swap in and out as needed. So I think that's what we should be thinking about when we're thinking about post-quantum encryption, is that the ability to adapt on the fly as needed as new technologies and new attacks emerge.
Yep. And, you know, there's not air quote military grade encryption. I mean, that's not, like you said, it's not really a thing. But we do have guidance from the federal government by way of like the CNSA suite, which is the Commercial National Security Algorithm Suite. So that's what the federal government uses and recommends for security conscious organizations. And that encompasses a breadth of different types of, you know, algorithms and families, including PQC, including ECC, RSA, et cetera. So I think we have good guidance in this space, but it does make sense for us to start thinking about it now, not during our next refresh cycle.
These are all very valid reasons why you shouldn't be rushing out to implement post quantum crypto algorithms today. However, tomorrow would be a really good time for you to take a look at it, because the more familiar you are with it and the way that it's being implemented in the various different areas inside of your software or inside of your data or whatever is more valuable to you, so that when you're ready to make that move, when you're ready to flip that switch, you're not struggling with implementation details. And kudos to the NIST for getting it right. Like, they didn't spend a whole lot of time going into the math behind it. There's papers if you want to read that. It's just like, hey, this will protect you a lot better in the future from the specific kind of attack that we know is coming, but we need to get a handle on it before it becomes an issue. And of course, if you want to learn more about things like post quantum crypto, the best place to do that is during our security field day events. We have one coming up October 16th and 17th. And I know for a fact that post quantum crypto is going to be something that gets discussed during that event. If you head over to techfieldday.com, you can see more information about that, and you can follow along with all the live streaming video. We'll in fact be joined by all of our guests here at Security Field Day, so we can't wait to hear what they have to say, and during the event and afterwards. And we would love to hear what you have to say. So thank you very much for being a part of the Tech Field Day podcast. If you want to leave a comment on this video, on your perspectives or your questions, please do so. You can also follow us on all of our social media platforms. We're at Tech Field Day almost everywhere. We'd also love it if you would subscribe to our YouTube channel and follow along with all the great events that we do at Tech Field Day. You can find out more information by going to techfieldday.com/podcast for the latest episode, as well as our upcoming Field Day event schedule. For more information about what we do here at the Future Room Group, please make sure you head over to futureroomgroup.com. You can also follow TechStrong TV for more episodes of content like this through all of those sister sites. We hope that you'll join us for Security Field Day, or at least watch the replay of the videos if you're watching this after October 16th or 17th. And we'll be in touch with more great information and more great podcast episodes very soon.